All right, in this lesson, we're going to finally start our discussion of trigonometry, which is one of my favorite topics. I like it because, frankly, it's a bunch of stuff about triangles, and triangles are relatively easy to deal with as far as basically all geometry goes. So we're going to start off with some stuff that is pretty much review of things that you would have done in previous courses. In fact, the very first thing is something that hopefully you learned way back in grade 9, and it's called the Pythagorean theorem. Now, despite the fact that it's called the Pythagorean theorem, most people can use it more or less correctly sometimes, but tend to miss the point of what a theorem actually is. So not that this is particularly important to the Pythagorean theorem, but it's important to theorems in general because it's something that students as a whole, including upper year and early university and college students, don't understand. And that's exactly what a theorem is in the first place. So a theorem isn't a rule, it's an if-then statement. It says if something is true, then there's a rule that can be used. The important part here is a lot of students like to memorize the rule without memorizing the if that is important for the rule to occur. So for instance, if I ask 90% of students what the Pythagorean theorem is, 90% of them are going to tell me that the Pythagorean theorem says that a squared plus b squared equals c squared. And it's not that they're entirely wrong, but the only thing that that applies to is a right angled triangle. So if you have a right angled triangle with hypotenuse C, and for those who forget what the other two sides are called, we know they're called A and B, but they're called together the legs, and it doesn't matter which is which. I can reverse the A and B and the theorem stays the same. And legs of A and B. So if that is true, and only if that's true, and this is important because it's going to come into play as soon as we do non-right angled triangles and people still continue to use the Pythagorean theorem because they say, well, you told me a squared plus b squared equals c squared. I only told you that's true for right angled triangles with hypotenuse c and side lengths a and b. But anyway, if that's true, then we have a squared plus b squared equals c squared. Okay, so it's not that it's really a hard thing to do. It's just I really want to make sure that you understand that theorems are not rules. Theorems are rules that apply in situations where the if part of the statement is valid. So I can't just walk up and say, well, you've got apples and oranges and cherries, so apples squared plus oranges squared equals cherries squared because I was told that if you just add up the sums of the squares and that should be equal to the square of the other one. I mean, obviously that's not true. Your shoe size squared plus your intelligence squared is not your height squared. It only applies to right-angled triangles. So make sure that if it's not a right-angled triangle, you're not using the Pythagorean theorem. All right, assuming these are right-angled triangles, which they are, and I can tell because they've got these little things down in the corner of each that show that it's a right angle. It shows a little square. If it was not a square, either there would be nothing there or it would be a curve, like a little part of a circle. But since they are, we can use the Pythagorean theorem. Now, I can change the variables a, b, and c. I mean, I could have written the theorem as x squared plus y squared equals z squared if the legs were x and y and the hypotenuse was z. In this case, I'm not even going to bother worrying about what I call them. I'm just going to say that we definitely have the legs of 5 and 12 and the hypotenuse of x. So the hypotenuse squared is equal to the one leg squared plus the next leg squared. That's 25 plus 144. That's 169. And if I take the square root of both sides, I get 13. More specifically, I get plus or minus 13, but I can eliminate the negative because it's a side length of a triangle and side lengths are not negatives. All right, for the second one, I'm going to be honest, a lot of people are going to jump into this one on the test and they're going to say, well, same question, Pythagorean theorem, 45 squared plus 36 squared equals x squared. But they would be mistaken. And the reason for that is that the unknown in this case is one of the legs, not the hypotenuse. And the rule says that if I take the two legs and square them, then I get the hypotenuse squared. Now at this point I'm going to pull out my calculator because I can't do numbers like 36 and 45 squared in my head very easily, but that one's 2025 and 36 squared is 1296. And if I quickly subtract 1226 or 1296 from both sides, I get x squared is 729. And then the square root of that is plus or minus 27. But again, I'm only concerned about the positive results, so that's all I'm going to bother writing down in this particular scenario. All right. The next question seems like it's similar, because it is, but it's not the same question. It's saying, here's a couple of triangles, and are they right angles or not? And I've done this on tests, and some students say they're not right angles because you didn't label them as right angles. And you're right, I did not. I did not put a little box down in the corner there. But that doesn't mean they're not right angles. It just means it's not labeled. I can't assume it's a right angle. So what I got to do is see if the Pythagorean theorem holds. So in this first one, I'm going to first start by noting that if one of these sides, if this is a right angled triangle, I don't know that it is, but if it is, this had better be the hypotenuse, 13, because the hypotenuse is always going to be the longest side. So what I'm going to do is I'm going to separately say, what is the sum of the two other sides, and what is the, sum of the squares of the two other sides, and what is the square of that side. So over here, that's 25 plus 121, and that's 146. And over here, 13 squared is 169. Now, in this case, the two numbers are not the same, so this is not a right-angled triangle. And because I'm a lazy mathematician, I'm going to show you the short form for writing a right-angled triangle. It looks like an L, but with that little right-angled symbol or square in the corner. So it's not right-angled. If you want to write down not right-angled, that's fine as well. But either way, it is not a right-angled triangle. I just mathematically proved that a squared plus b squared is not equal to c squared. All right, the next one here, I'm going to be honest, doesn't really look like a right-angled triangle. The first one kind of at least looked like it. This one doesn't. But you got to remember that not all diagrams are perfectly to scale or drawn accurately. We have to go with what we know in the thing, or in the actual math. Here, again, if there is a hypotenuse to a right-angled triangle, it's going to be the longest side, the 26. So what I'll do is I'll separately do the sum of the squares of the other two sides. And separate, I'll do the square of 26. Because the 26 is shorter, I'll do it first. And the answer to that is 676. And then the other one over here is 100 plus 24 squared is 576, which, is 676. So it is a right-angled triangle. In fact, I can now say it is definitely a right-angled triangle. So the one that looked like it wasn't, the one that didn't look like it was, again, the diagrams are there just for our kind of, to roughly see what's going on, but they're not necessarily always accurate. All right, moving right along. We learned another tool. You would have learned it in grade 10 and or 11 and or wherever else you were. But either way, you should recall there was a rule called SOHCAHTOA. And I'm just going to make a little note up at the top here for those of you who don't remember what it stands for. But SOHCAHTOA says that the sine of an angle is equal to opposite over hypotenuse. The cos of the angle is equal to the adjacent over the hypotenuse. And finally, the tan of the angle is equal to the opposite over the adjacent. And I should point out that SOHCAHTOA, again, just like Pythagorean theorem, only applies to right-angled triangles. That doesn't mean we can't use sine, cos, and tan in them. It just means that there is no opposite, hypotenuse, or adjacent in a non-right-angled triangle, so we can't use it this way. So in the first one here, the first thing we want to do really, you'll notice there's no numbers. We're not concerned with this particular question at this point, but what we want to do is just make sure that we identify which side is which. So for starters, the hypotenuse is always going to be the one that is across from the 90-degree angle. The opposite and adjacent, just for those of you who are not familiar with those words really and how they apply in the English language, to be adjacent to something means that you're beside it. If I'm adjacent to a friend, I'm standing beside my friend. So what that means is that the two sides, we have this one and this one, only one of them is beside the angle. Now technically there's two sides beside the angle, but one of them is the hypotenuse. The other one is the adjacent, which I'll just call A. And then the opposite, if I'm sitting at a table opposite someone, it means they're sitting across from me. So that would be the one over here. That's the opposite. Now again, which one is opposite, which one is adjacent depends on which angle you're referring to. If I referred to this angle down here, instead of calling it theta, I called it, I don't know, alpha or something like that, then the opposite and adjacent relative to alpha would be reversed because the side that I listed as opposite is actually adjacent to alpha, and the side I listed as adjacent is opposite to alpha. So again, it's highly dependent, the opposite and adjacent, on which angle it is you're looking at. The hypotenuse is always the hypotenuse. Just quickly doing the same thing with the second one, the hypotenuse is the easy one to tell. The opposite is the one across from it, and the adjacent is the one beside it. And just like Pythagorean theorem, this only applies to right-angled triangles. Oh, I almost didn't fit it in there. Okay. So only right-angled triangles. If it's not right-angled, this will not work. And every time I teach this course, about a quarter of the class will use it on non-right-angled triangles, and then they're confused why the answers don't turn out right. So make sure it's a right-angled triangle before you apply it. All right, so now that we kind of get how SOHCAHTOA works, let's use it. We want the x here is our unknown. And I'm just going to make a little quick note on here. You don't have to if you don't want to, but I'm going to note that relative to the 32 degrees, this side is the opposite, the 12 is the adjacent, and the x is the hypotenuse. Now, I don't know or want the opposite, so I'm going to ignore that. I'm just going to look at the fact that I want the hypotenuse and I have the adjacent. And then I think about SOHCAHTOA. SOHCAHTOA, and I ask myself, which of those three trig ratios, sine, cos, or tan, has an adjacent and a hypotenuse in it? And that would be the second one, cos. So I set this up as cos of 32 equals the adjacent divided by the hypotenuse. Now this one's a little trickier than sometimes they may be because the unknown is on the bottom of the fraction, but that's okay. All we have to do is do the same thing to both sides of an equation, and we can get x by itself. And what I'm going to do actually is start by multiplying both sides by x, and that gives me x cos 32 equals 12. And then I'll divide both sides of the equation by cos 32, and that gives me 12 over cos 32. And finally, if I just throw that into my calculator, 12 divided by cos of 32 equals 14.15. Now, if you rounded that off a bit, that's okay. I'm not too worried about that. There are no units given on the triangle, so we're just going to say it's 14.15 units. And then what we're finally going to do before we move on to any other questions, something we should normally do in all math, is look at our diagram and see that number makes sense. So we can see the adjacent is 12. We know the hypotenuse is longer. 14.15 makes sense. If you screw up, you choose the wrong ratio or you do something upside down or backwards, typically your answer will be like a ridiculous thing and you'll kind of notice it there. So in this case, if you get a hypotenuse of like 9, you should know that that's wrong because the hypotenuse can't possibly be shorter than 12. And likewise, if you got a hypotenuse of like 300, you would look at this and say, I don't know, that feels really, really out of whack given that the adjacent, which appears to be the longer side and actually is 12. I can't imagine the hypotenuse being that large. So just make sure your answer looks reasonable before continuing. All right, the second one, we'll do the same thing. We're looking for that x there. In this case, we're dealing with this 52-degree angle right there. Relative to the 52-degree angle, the 31 would be the adjacent, and the x would be the opposite. The hypotenuse is up here, but we're not asked for it, nor are we given it, so it really doesn't matter within our question. It's not something we need to know or worry about. What we do need to do is find the trig ratio that uses both opposite and adjacent, and that would be the tan. So the tan of 52 degrees equals the opposite, which is x, divided by the adjacent, which is 31. And what you can do that is just multiply both sides by 31, and you'll get x by itself. Just be careful when you're punching this in your calculator. Depending on your calculator, you may have to do 52 and then hit the tan button, or you might hit tan first and then put in 52. If you're getting answers that are different than mine, you'll be able to figure it out pretty quickly which way your calculator works if you didn't know already. But either way, I'm going to do the tan of 52 times 31, and I get 39.7-ish, we'll say. So 39.7 units. I'm going to look at this and say, does that make sense? The adjacent's 31. The opposite apparently is a little bit bigger. Well, if this is a 52-degree angle right there, if it was 45, the opposite and adjacent would be basically the same. But because 52 is larger than that, the opposite should be bigger than the adjacent. And sure enough, it is actually a little bit bigger than the adjacent. So no surprises. All right. The next is solve for the unknown angles. So we just solved for a couple of unknown lengths. Now let's do something very similar. I'm looking for the theta in each of those. Relative to my angle theta, 15 is going to be the adjacent, and 34 is going to be the hypotenuse. I'm not even going to bother listing the opposite because frankly it really doesn't matter within the question. So we're looking for, and if it helps you to write it out each time, go nuts. SOHCAHTOA. The more you write it, the more you'll remember it. We're looking for something that has an adjacent and a hypotenuse in it. Again, I think that's going to be the cosine. So this time we set it up just slightly differently. We don't know the angle, so we put cos of theta equals adjacent of 15 over hypotenuse of 34. At this point, you can do cos of theta and just simplify that. 15 over 34 is 0.441. In fact, for angles, I think I'm going to try to do 4 decimal places, even though I sometimes forget. But we have that number there. Now, the good news is you're not going to clear it from your calculator anyway. I'm going to just kind of do a little aside here to show you that what the proper mathematical form would be. Technically, what we need to do is the same thing to both sides of our equation, which means that I need to take the cos -1, or the inverse cos of cos theta, and I do the cos -1 then of the 0.4413. Trying not to get too much into the area for my next triangle there, but either way, and then that gives me theta equals whatever the cos of the -1 or the inverse cos of 0.4413 is. I never actually write out that full notation. It's kind of tedious. So I'm just going to go back down here and say, I'm just going to write down theta on the left-hand side after I've, by the way, this is bad math slang. It's not official, but I use the term uncos. I'm uncosing that side to get the theta by itself, so I'm going to uncos the 0.4412. That doesn't mean I punch in cos of 0.4412. It means I take the 0.4412, and then I do, on most calculators, it'll be inverse cos, or second function cos, or shift cos, depending on what button it is that does the line above the buttons. But on my calculator, it says second function, so I'm going to second function cos that, and I get out 63.8 degrees. I'm going to round all my angles always to 1 whole degree, so 63.8, I'm just going to write as 64. The only applications that it would really matter if you were keeping decimal places in degrees would be things like architecture, or if you're like a sniper, it would make a difference. But for most math, the closest degree is pretty good. Um, this is a little bit hard to understand, but compared to significant digits with regular numbers, like for instance, rounding off a number that's like between 1 and 10 to the closest digit introduces significant rounding error. Rounding off numbers that are in the millions to the closest full whole number means almost nothing. But as it turns out, that when you're dealing with like angles, um, 1 degree is 1 degree. So whether you round off, 1.3 degrees to 1, or 321 degrees, 321.2 degrees to 332, whatever that is, we kind of are rounding with the same accuracy. It's basically a direction. So it doesn't matter whether it's a small number of digits or a large number of digits, whether it's, like I said, 7 or 327. It's the same accuracy to round off to a whole digit. Okay, anyway, that said, we're going to look at the diagram now and just see if that makes sense. 64 looks like a pretty big angle. That means that 15 will be the short side. This one will be longer than 15. I don't know what it'll be, but it'll be longer than 15. And 34 is the hypotenuse. Seems like it would make some decent sense. All right, moving on to the second triangle. For this one, we have our angle theta down there. The 43 is the hypotenuse, and the 18 is the opposite because it's across from it. I look up to SOHCAHTOA and I see that sine is opposite over hypotenuse. So sine of theta equals opposite over hypotenuse. And then I'm going to do this actually all in one step in my calculator. 18 divided by 43 is 0.4186. There's really no point in writing that down. And then what I'm going to do is do the second function sign, the inverse sign, the shift sign of both sides. Now my calculator, second function sign, and it gives me 24.7, or about 25 degrees. And again, I look at that and say, well, if the angle down there, theta, is 25, that's a pretty small angle, which means this one's going to be the shorter side of the legs. This one's going to be the longer side of the legs. And the short one is 18. The longer one's bigger than 18. A hypotenuse of 43 doesn't seem too unreasonable. All right, assuming we're doing okay with that, let's shoot into some word problems. Again, some word problems are more realistic than others. I feel like this one's a little bit fictitious, but hey, let's go with it. A small town has hired a construction company to build a road to connect a town to another town that is on top of a 20-meter tall cliff. Interesting. The new road will be 200 meters long diagonally and will rise vertically 20 meters above the length of the road. Draw a diagram of the situation and calculate the angle of elevation of the road. I'll talk more about angle of elevation in a moment, but basically we're down here at our city, we'll call it, I don't know, city A. And we know that there's going to be a road that goes up to the top of the cliff here, and that's going to be to city B. And we do know that that road is 200 meters long. And we know that the elevation of that road is 20 meters. Guess we can put units on there if we want. And also, since it's 20 meters high and height is measured relative to the flat ground, we can say that that's going to be a right-angled triangle. Okay, so what it's looking for is an angle of elevation. So we'll pretend that we're over here in our city A. Angle of elevation basically says how far do you have to look up as an angle to see B. So we start here and we go up to there, and that's our angle of elevation. We'll talk more about angle of elevation and angle of depression later, but for now I'll tell you that both of them are always going to be measured relative to horizontal, not vertical. So it's basically how far you look up from the horizontal or how far you look down from the horizontal. In this case, definitely an up. By the way, someone in B would have an angle of depression down to town A because they're looking down from their position. Either way, once we've got this, we have an unknown angle, but we do have a known height, and in this case, height is the opposite of the angle. Ugh, excuse me. I need a drink. Diet Coke fixes everything. Okay, 20 degrees is our opposite, or sorry, 20 meters is our opposite, and our 200 is the hypotenuse. All right, so once we know that we're dealing with an opposite and a hypotenuse, so ka toa so sine is opposite over hypotenuse. So sine of theta equals opposite over hypotenuse. If you want to take this step, you're more than welcome to. This one's easy at least to write down. 20 divided by 200 is 0.1. And now you put the inverse sign into your calculator, whether that's an inverse button, shift, or second. I usually refer to it as inverse or second. Inverse because that's actually technically what it is, and second because that's what my calculator says. Either way, the inverse of sine for 0.1 is 5.739. Now in this application, there may actually be a good reason to keep an extra decimal place, but because we're just high school students and we're not designing a real road, I think it's safe to say that the angle's about 6 degrees. So that's it. Angle of elevation is about 6 degrees for that problem. All right, let's do, I think, just one more, then I'll let you do some practice problems. A 12-foot ladder is leaning against a wall. The foot of the ladder makes an angle of 68 degrees with the ground. How far up does the ladder touch the wall? So I'm going to just kind of draw this diagram here. Oops. There we go. There's the wall and the ground. By the way, this is kind of a physics thing, but in physics we sometimes do this to show that that's like the solids. The ground is solid going down, the wall is solid going to the left. And then we take our ladder, and just because I feel like it, I'll put it in a different color. There's our ladder. And we're told that it makes an angle of 68 degrees with the ground. So that's going to be there because the other angle up in the top would be against the wall. And we are told that it is a 12-foot ladder. We want to know how high up the wall it goes. That would be, we'll call that h, or you can call it whatever other variable you like, but I like using h. And basically now we just have to set this up. So relative to the 68, we know that this is the hypotenuse because it's the longest side, and the h is going to be the opposite. And as it turns out, opposite and hypotenuse again will be our sine. This time though, the sine is of a known angle, so we'll do sine of 68 degrees. And we're going to do opposite h over hypotenuse 12. To get the h by itself, multiply both sides by 12. Anytime I get something equals a variable, I always just write down variable on the left-hand side in my last step. Either way, you're just punching in 12 times the sine of 68. And I'm getting 11.13-ish. And again, if it was a test and you rounded that off to 11.1, that seems pretty reasonable. If you round it off to 11, I'm probably not going to mark it wrong or anything like that. But we're starting to kind of lose, well, 13% of a foot. And since this is only a foot lower than the length of the ladder, I think losing 13% of that foot might be a little bit of an issue. But either way, how high it goes up the wall, 11.13 feet. As far as therefore statements go, as long as you have answered the question and it's clear what your answer is, I will give you no hassle. If your answer to the math is not actually answering the question, then that's a separate issue. Then you might want to do a therefore statement to be clear what it is that the actual answer to your problem is. All right, there are some practice problems here for you to try, some triangles to work with. and a couple real world situations-ish things. Answers are down at the bottom. They're provided for you. I will point out that if you printed this off to work on, you may find that there is not a whole lot of paper space to write in your answers. You may want to do this on a separate sheet of lined paper or write extremely small. Either way, that's completely up to you how you complete it. But try those problems, check the answers at the bottom, see if you're doing them correctly. If you are, that's fantastic, and you clearly don't need my assistance. If you're getting answers wrong and you're not sure why, then by all means reach out and I will see what I can do to help you. Otherwise, I'll say goodbye and we'll see you in the next lesson.